Question 42. This type of question comes up reasonably frequently, and it's quite confusing at first, I think, or at least people seem to find it that way. When it's talking about planes of rotation, in part C where it's talking to an axis through XY, it's as if it was rotating on a spindle that goes through this way, so it rotates out of the page and back down again, so that it cuts right the way across that magnetic field. So sometimes the field lines are going through the loop, and at the moment they're parallel to the loop. If it was rotating through Z, it would be spinning around like that, and it still wouldn't be linking with the field because it would always be parallel to it. So the only way to induce an EMF in this is if this coil links with the field, so it needs to rotate around XY, which is why I mentioned it at the start. In question 43, the positively charged copper ion enters the magnetic field. We need to use Fleming's left-hand rule to work out the direction of force on it. The current is in the direction of the copper ion, so I'll use my middle finger thinking of that. The magnetic field is up the page, and my thumb is pointing out of the page, so the initial direction of the force that acts on the ion is out of the page. The subsequent path of the ion, including a qualitative description and a calculation, well, the path is going to be a circle, a vertical circle coming out of the page. So it moves in a circle out of the page. It then wants us to calculate the radius of the circle. That's what the calculation bit is about. So to do this, we have to equate the force, the magnetic force on the ion, with the centripetal force for circular motion. Straight away we can cancel a V, and by rearranging we get the radius is equal to mv over bq. Now we know in this case that the mass of the ion is 1.05 times 10 to the minus 25, and the velocity of the ion is 7.8 times 10 to the 5 meters per second. It tells us the magnetic field is 0.28 Teslas, and it says it's doubly charged. Doubly charged means it's plus 2, so 2 times 1.6 times 10 to the minus 19, and that comes out as a radius of 0.91 meters. For part B, we need to keep in mind the formula that we derived, R equals mv over bq, and if the magnetic field B is doubled, this would halve the radius, so the radius would be halved. If a singly charged ion replaces the original one, which was doubly charged, that would halve Q. If we halve the bottom, that will double the radius, so radius would be doubled.